thanks to Les for inviting me. I met Les at ASPW, Advanced Space Propulsion Workshop. I think it was last year in Colorado Springs, and I've been involved in the interstellar field for about a decade now. I did my master's degree thesis on exotic propulsion. That's when I first got exposed to Mark Willis's Breakthrough Propulsion Program, for example. First got interested in the work of Miguel Alcubierre and his stuff on warp theory and other such stuff. And met Claudio in 2001 at the first field propulsion conference in Brighton. And so I've been sort of involved in the field, like I said, for about a decade now. And you know, the last few months have been a very exciting era, I think, for everyone involved in interstellar research. I mean, the DARPA 100-year Starship, which I think we all heard about, has really galvanized the interstellar community and created this buzz of activity. And so obviously this is $500,000 of seed funding, which they're offering for an organization not to build a starship, but to create the machinery, to create an organization that will be able to stand the test of time, to create a multi-generational, pan-decadal company. Now, one thing to keep in mind is that the average lifespan of a company in the United States is about 13 years. And so what DARPA want to do is seed fund an organization that could last 100 years, which is about the amount of time that we're estimating. It's going to take us to develop, go through that technology roadmap, increase the technology readiness levels of certain technologies that we're interested in today, fission propulsion, fusion propulsion, beamed energy propulsion, and so forth. And so another thing that they really want to do is, once they've given this money away, they want to move away from government funding. We have very capricious programs start, programs stop. Congress doesn't like something, and what they want to do is sort of really give this over to the next Google or to the next Apple. I mean, I don't know if any of you saw in the news recently, but Apple had more spending money available to it at one point than the US government. It had sort of $74 billion sitting there. So, the aim of this $500,000 is to seed fund an organization that's perhaps going to be that next Google or Apple, but it's going to divert resources to funding people like you and I who are interested in manifesting that dream of interstellar propulsion. And so I've been privileged for the last couple of years to be involved in a project called Project Icarus, and more recently we founded a non-profit foundation, Icarus Interstellar. And so I'm going to be talking a little bit about that today. So really the structure of my talk, and this is a perturbation of a talk that I did give in Orlando last month, and more recently with Al Jackson, who invited me to the AIAA Lunch and Learn workshop last week, I think it was, in Houston. And so I'm going to say a few words about the physics of interstellar travel. Why is this such a challenging problem? I mean, we've sent human beings to the moon. Well, it's a very difficult problem, so I'm going to try and articulate that. Then I'm going to go into the details of Project Icarus, what it is we're working on, and what the non-profit foundation is sort of focused towards. And then, if there's time, then I'll say a few words about specific Starship designs. There have been a few detailed studies in the past. We had a little bit from Les today, for example, about Project Orion and Project Daedalus, and so we'll go into a little bit of the technical details of those projects. So let's talk about just the enormity of this problem. As was mentioned earlier, back in the late 70s, 1977, the Voyager probes were launched. And they are to date the farthest and fastest spacecraft that humanity has ever launched. Traveling at 38,000 miles an hour, Voyager 1 is 116 astronomical units from Earth. Let's give a beautiful example of turning things into feet. What I'm going to do is give an example in terms of the United States. And let's say that we shrink the scale down and we locate Earth in New York City, and we locate Alpha Centauri, 4.3 light years away, over in Los Angeles. Well, where is Voyager currently on its trip from New York to Los Angeles? It's traveled just a single mile in that trans-American trip. So it's taken 34 years just to travel a single mile in that 2,500 or so mile trip. And so obviously it's a problem of distance. And what we want to do is travel much faster to get there. As Les alluded to, it's going to take on the order of 50, 75,000 years, I think it is. And what we really want to do is increase the velocity by a factor of about 1,000. so we can reduce the travel time to be consistent with timescales of a human lifespan. You know, we would like to see the fruits of our labor. We would like to send a probe and see it reach its destination and receive that information. You know, this isn't something for our great to the nth degree grandchildren. We want to see the fruits of our labor. So that's really what we sort of want to focus on. Now, the challenge becomes more apparent if we consider one of the most elementary equations of rocket science, the Tsiolkovsky rocket equation. And it relates the payload, the fuel to mass, the mass ratio of the fuel to the structure on the left-hand side, which are denoted by R, to how fast you want to travel, or more specifically the delta V, and to the specific impulse of the fuel that you're using. Now, if you want to travel to, say, Alpha Centauri in about timescale of human lifespan, you need to be traveling at about 10% the speed of light. And so when you plug in 3 times 10 to the 7 into the delta V, which is 10% the speed of light, and you stick in the value for the specific impulse of a traditional chemical rocket fuel, it's about 460 or so seconds for the space shuttle fuel, what you get is that you need more rocket fuel mass than there exists mass in the entire universe. I think that's an absolutely remarkable result, but what it demonstrates is that a single-stage chemical-propelled rocket engine is never going to reach the closest star on timescales of a human lifetime. It's a physical impossibility. And so we have problems and challenges that we need to overcome. Fortunately, chemical rockets aren't the only way to go. I mean, we're a clever species. You know, we understand physics, and what we've started to, really appreciate roughly, last century or so, is that rather than extract energy from the creation or destruction of chemical bonds, which is how we liberate energy for chemical propulsion, that if we journey into the nucleus of the atom and we move into the field of fission, where we sort of, rip the nucleus of a high atomic number particle apart, or fusion, where we fuse together light elements, we see that there's far more energy that we can liberate. And so this really table sort of put things into perspective. So, what we have here is the type of reaction, and what the maximum amount of energy we can extract, we believe we can extract from that reaction. So for chemical energy, 1 kilogram, you can typically extract about 15 million joules of energy. But when we make the jump from chemical to fission, you see that we go up by a factor of about 1 million. So for a single kilogram, we get about 1 million times more bang for our buck. For fusion, that's a 10-fold increase on fission. And so, we get 10 million times more energy than we do from chemical energy. And then antimatter, which was alluded to earlier, that is when particles and antiparticles meet and annihilate each other perfectly, according to Einstein's E equals mc squared, we get 9 times 10 to the 16 joules of energy per kilogram. So we know that there are techniques out there that we don't need, for example, warp drives or wormholes, that there is known physics that will allow us to liberate far more energy and perhaps one day be utilized for propulsion. So let me tell you now a little bit about Project Icarus. So it's, and I need to tell you a little about the name as well. So sometimes people say, well, why are you calling it Icarus? Wasn't he the guy who flew too close to the sun and his wax wings melted and he died, and it's an expression of human hubris? But what we like to think, well, first off, it's the successor of Project Daedalus, and Icarus was the son of Daedalus, so we want some consistency with the name there. And also we like to think of Icarus as a pioneer, someone who pushed the machines of his day to their limits, and in doing so, revealed their hidden faults and allowed engineers and creators of the future to build bigger and faster machines. So Project Icarus was inspired by Project Daedalus, which ran from 1973 to 1978, which was conducted by the British Interplanetary Society, which was, at the time, probably the most detailed interstellar starship study that was ever done. And it was a volunteer study, which is what Project Icarus as well. So our team, we've got about 30 team members. We're distributed all across the world. We've got someone up here in Alaska. We've got a good nucleation of team members in the United States. We have a large representation in Europe. We have a guy in Cyprus working on some of the computer technology that we're interested in. We have a student designer in India, and then we have someone way down in Australia. So this is really a sort of pan-national project. So what are the terms of reference? So this is what we're doing. So it's a 5-year theoretical design study to build an interstellar unmanned robotic probe that could potentially decelerate in the target system, and that's sort of one of the main differences from Daedalus, which was just a flyby mission. So flyby missions are, great. I mean, there are certain steps that we're going to have to take before we go to the stars, and one of them is going to be precursor missions, perhaps to the Oort cloud, to the Kuiper belt, to 1,000 astronomical units, to 10,000 astronomical units. Possibly the first interstellar mission, possibly it'll be a flyby. Ultimately, what we're going to do is slow down, though, because if you think about a flyby mission traveling at about 10% the speed of light, it's going to whiz past Jupiter in about 3 seconds. It's going to whiz through that solar system incredibly rapidly. And by the time we reach the stage where we could launch an interstellar probe, 50, 100, 200 years from now, I'm not going to try and predict things, but it's very likely that we will have telescopic technology here on Earth or on the Moon that would be able to acquire as much data as a rapid flyby of the target system. So what we really want to do with Icarus is rendezvous, so interstellar rendezvous mission. So here is really sort of the foundations of our project, what we're attempting to do. We want to design an unmanned probe that's capable of delivering useful scientific information about the target star and hopefully any associated bodies around that target star. And I think we're in an incredibly exciting period now. I mean, I read an article recently, we discovered something like 760 exoplanets, and so it's really getting more and more exciting. We're starting to realize that the galaxy is rich with planets, and that, what's the next step? Well, maybe there are some out there that are Earth-like, that are in the habitable zone. What can we learn about them? So that's one of the things we're very interested in. We want to use current or near-term technology. I mean, we want this to be a credible design study. I mean, like all of you, I'm very excited by some of the stuff we're seeing on the edges of theoretical physics now. But, until we sort of see some experimental evidence, I mean, for FTL, I mean, we've got the argument going on now with the neutrinos, but we want to use stuff that we know works that's at a reasonably mature TRL level. 2 or 3 perhaps, but something that we can progressively mature. And stuff like warp drives and wormholes don't even exist on the TRL level naturally. We want to reach the destination in a timescale not exceeding a century. Now, Daedalus actually had a stricter timescale. I mean, they were going to reach banana star in about 57 years. We've relaxed that a little bit, and I think that makes our mission a little bit easier. There's a relationship. So we want to allow for a variety of target stars because every month almost it seems like we're discovering new planets. So during this study, we don't want to fixate on Alpha Centauri or Epsilon Eridani too early on in the study in case we discover something more interesting at 6 or 7 light years, for example. And like I said, we want to design a craft that has some deceleration in the target system, preferably a full rendezvous, and that's sort of an ongoing debate within the team. This is how we've really split up the research modules. We've demarcated the project into 20 research areas that we think are the salient features that should be studied for an interstellar probe. So for example, we have someone studying the astronomical target, where we want to go. We have someone, we have primary propulsion, secondary propulsion. What kind of fuels are we going to use? What kind of power systems? What's the communications going to be? We're very excited by the work of Claudio and the focal research. I mean, this is something one of our guys is actively looking at. Navigation and guidance, and so on and so forth. What kind of science are we going to do when we get there? And we've assigned module leads to each of those modules, and those module leads have a team working underneath them. And what we've done is sort of, we've given ourselves a number of trade studies that are really educating the team up to the level where we can, comfortably down select in terms of the design of the probe.